Hello, good afternoon, everyone. Welcome once again to our seminars of the Astronomy Department. Today, we have the pleasure of having with us Dr. Florencia Vieyro. We are very pleased to having her with us today, sharing her work with us. Florencia had her bachelor and master degree in astronomy in La Plata University. She also had her PhD diploma from La Plata University, but she also was a sandwich fellow here in Unicampi. She made a postdoc research in the Radio Astronomy Institute, Instituto de Radioastronomía Argentina, in Argentina, and then she did a postdoc at the Universitat Barcelona. Currently, she's an associate research of CONICET in the Instituto Argentino de Radioastronomía, and she also teaches at the La Plata University. Her work is mainly focused on high-energy astrophysics, non-thermal processes, particle acceleration and transport, neutrinos, black holes, jets, general relativity, and high-energy plasma phenomena in general. And today, Florencia will present on the interaction of extragalactic jets with obstacles. And I will ask everyone, please turn off the camera during the presentations and the microphones. And the questions will be done after the talk. And if you have one question, please indicate this in the chat here or in the chat of the YouTube channel. So, well, Flor, whenever you want, you can start presenting.
Well, thank you, Maria, for this nice presentation, and in particular for the invitation to present this talk. I will start sharing my screen. Oh, here. Share, 1 second. And I think I'm sharing now.
Yes.
And presenting.
Yes,
here
perfect.
You can see my cursor, right?
Yes, we can.
Okay. Well, as I say, thank you, Maria, for the invitation to present this talk. And as Maria said, I'm going to talk about the interaction of extragalactic jet with obstacles. I'm going to describe briefly some of the works in the literature that study this interaction, and also I'm going to describe some of my work in this subject. This work I kept doing with people from the University of Barcelona, where I did my postdoc with the group, the High Energy Astrophysics, as Maria mentioned earlier. So, as you all probably know, relativistic jet is a phenomenon that is found in several sources in nature, and in particular, it's found in some of the most powerful sources in the universe. And this phenomena is associated with the accretion of matter into compact objects, and in particular into black holes for some of these sources. One of these sources are active galactic nuclei, which is powered by the accretion of matter into the supermassive black hole in the center of most, if not all, galaxies in our universe. Here we can see an image of the radio galaxy Cygnus A, where these relativistic jets are found in red. Here is the very collimated part, and these jets ends into bright hot spots. On smaller scale, in galactic scale, we found the X-ray binaries, or in particular MICROQUASARS, which are X-ray binaries where the jet is detected, mostly in radio wavelengths. And these sources are powered also by the accretion of matter, but in this case into a compact object that can be either a neutron star or stellar black hole. And the material is is coming from a companion star. And we also found relativistic jets in these gamma ray bursts, which are very powerful sources. And again, the basic ingredients are the same. We have a matter that is available and it falling into a black hole. In this case, a black hole that it was formed after the collision of two compact objects for the case of short GRBs, or is the result of the evolution of a Wolf-Rayet star in the case of long GRBs. But again, as I said, the ingredients are more or less the same. We have a material available that is being accreted into a compact object, and these jets are launched and produced. There are also another astrophysical sources that present jets. Some of these are very recent, like tidal disruption events, which are events in which a star is disrupted by tidal forces because it's approaching a supermassive black hole. And we also find jets in young stellar objects, although these jets are not relativistic like the other four I mentioned earlier. But again, the ingredients more or less of the process is the same. We have a matter and that is falling into an object. In this case, it's not compact, it's a star, but it's falling into this object. It's formed in an accretion disk. And this is responsible for collimating and launching the jet. So in my talk, I'm going to focus on these astrophysical sources, galactic nuclei, and the relativistic jets that they are produced in these sources. So, as I said, the ingredients of this process is more or less the same in the different sources. We have a compact object. In the case of AGNs, it's a supermassive black hole in the center of galaxies. That is accreting material. This material forms an accretion disk, and a mechanism probably of magnetic origin is responsible for launching and collimate two relativistic jets. As I said, I'm going to talk about the jets we found in AGNs. This is more or less like a cartoon of the classification of AGNs, and is usually called like AGN2 because the classification of these sources is very complex and depends on several parameters. For my talk, the main parameter that I like to pay attention to is the inclination of the jet, because we call it blazar when the jet is pointing towards the observer, and we will call it radio galaxy when we are observing the jet in the same plane of the sky. The phenomenology of the AGN also depends if we can see the inner region of the AGN, where there will be different lines in the spectra. It also depends on the power of the jet. So we made this classification in radio loud for more powerful jets and radio quiet AGN. But as I said, of all these very complex classification, I only want for you to remember is that I will call blazar to those where the jet is pointing towards the observer, and in those cases we are going to have a Doppler enhancement of the emission because of relativistic effects, and we call them radio galaxy to those AGNs where the jet is in the plane of the sky, as the AGN I showed a few minutes ago. So during the last decade or so, it has been well established that the presence of a supermassive black hole in the center of galaxies, and in particular the activity associated with this object, plays a fundamental role in shaping and the evolution of the galaxy as a whole. The main reason that supports this idea was the discovery of the M sigma relation, which is an empirical relation between the the mass of the black hole in the center of the galaxy and a measure of an estimation of the mass of the whole galaxy. So this relation indicates that there is some mechanical feedback and in exchange of energy between the black hole and the galaxy that links their their growth, and these masses are related. So this is called this mechanical feedback is called AGM feedback, and now we know that it operates in different modes, and one of these modes is called the kinetic or radio mode, in which the launching and the produce of these radio jets reheat the gas in the galaxy and regulate the star formation and also the growth of the galaxy as a whole. So the presence of this supermassive black hole, and in particular the AGN activity, shapes the galaxy and the evolution of the galaxy host, but the influence is also goes the other way around. We know that the center of galaxies are media very complex, often filled with dust, gas, stars, globular clusters, different type of clouds. So the media where the jet is propagating, that is basically the nature of the galaxy host, can impact the propagation and the morphology of the jets. So there have been several works studying the possible interaction of a jet with different obstacles it can encounter during its propagation. So I'm going to describe some of this work, and in particular, I'm going to describe some of the work I have been doing in this subject. Sorry, I was using the other mouse here. So this is the dichotomy found in the morphology of radio galaxies. As I said earlier, radio galaxies are those in which the jet is in the plane of the sky. And we found this dichotomy where FR1 galaxies present a jet that scale of kiloparsec is already disrupted. It has expanded sideways and it doesn't keep its form. Whereas the more powerful FR2 galaxies have a very highly collimatic jet that propagate beyond the kiloparsec scale, and they end up in two bright hotspots as the one I showed you earlier. So it has been proposed that some of the reason for this dichotomy might be the mass loading of the jet by the interaction of jet with stars with strong stellar wind. I think that the most numerous obstacle that a jet can encounter is stars on its path. So there are earlier works of 1994 of Komisarov and also from 1996, where they already started to study the effect that the population of stars might have on the dynamics of the jet. For example, if we study the stellar evolution in an elliptical galaxy as M87, we can see that at this day, this galaxy may have like 1 million of red giant stars inside the jet at any given time now. So this is a very numerous obstacle. It may have an impact on the dynamics of the jet. In particular, normal type stuff won't affect the dynamic of the jet, but those stars that are relevant for this interaction are those that present a strong stellar wind, such as red giant star or more early type of star like OB star or Wolf-Rayet with strong, powerful winds. More recent works that develop numerical simulation of the impact of the presence of these stars inside the jet and how it can affect the dynamics show the effect of mass loading over weak relativistic jets. I don't know if you can see the graphic, but here in this plot, which is the most interesting one, here we can see the velocity of the jet when the effect of mass loading is not considered. Here we can see that it's propagating always at the same velocity, but when they include the effect of mass loading by stellar winds in the jet, we can see that the jet starts to decelerate. So this interaction actually have an impact on the dynamic of the jet. Although this author found that this effect is only relevant for very weak jets with power of 10 to the 42 Earth per second or lower. The mass loading by stellar wind have no impact on the dynamic of more powerful jets with luminosities of 10 to the 44 or above these luminosities. In these cases, it is thought that the mass loading takes place by mass entrainment from the shear layer, which is not consistent with mass loading from stars. So there is this work that study this entrainment from the shear layer of the jet and might work for decelerate more powerful jets. So this is from a theoretical point of view. What is the evidence that we have that this interaction may actually be taking place? So from very early on, from 1979, and more recent work by Harkassen and corroboration, they show that the bright hotspot found in the jet of M87 are sites where particles should be accelerating in situ. So they have proposed that some of the bright hotspots, not all necessarily, but some of them might be the interaction of the jet with obstacle in its path. But this is like an indirect evidence, if you want. A more direct evidence has been obtained in the jet of the galaxy Centaurus A, where with BLBI technique they observed the changes in the morphology of the jet along the years, and in one particular time they found that the jet is like bifurcated, and they attributed this change to the interaction with an obstacle. In particular, they proposed that it was a star. So this is like the most direct evidence that we have that this type of interaction may take place actually. So the dynamical evolution of an obstacle that enters the jet is very complex, and there are many numerical simulations to study this evolution. The basic idea is that when an obstacle enters a jet, it could be a cloud or a star, but let's take a cloud. The impact of the jet will cause that the cloud starts accelerate because it will transfer momentum, but it also will hit the gas of the cloud. So the cloud will start to expand sideways, but also the pressure gradient exerted by the jet, by the impact of the jet, will produce an elongation downstream. And the clouds also will develop Kelvin-Helmholtz instability because of the impact of the jet, and also Rayleigh-Taylor instability can develop in the surface impacted by the jet. So eventually, after the expansion of the cloud and the heating of the material, we expect that this instability will start stripping material from the cloud and will disrupt it eventually. As I said, this is a very simplified vision of this interaction, but there are a lot of simulations that confirm this very simplified vision. Of course, that it will depend on different factors. Of the evolution of the cloud will depend on different factors: the magnetization of the jet, the conductivity, and a lot of other effects that we have to include in this study. But the basic idea that I want you to have is that the cloud enters, it will expand, it will be elongated downstream, and we start losing material from instabilities, and eventually it will be disrupted. These are some of the work that study this interaction with different type of clouds. And last year, well, actually the year before that, we asked ourselves, what would be the effect of having like the most massive obstacle that the jet could encounter, which is a supernova remnant. So we studied the evolution of a supernova remnant inside a relativistic jet, and we base our study on in previous work by Barkov and Gangulian and collaborators, in which they study how is accelerated an obstacle that enters in magneto-hydrodynamical jet, and they study how this obstacle is accelerated by the jet run pressure. We did the same, but we consider in hydrodynamical jet because we are interested in studying the possibility of having a supernova inside the jet, and that is more likely to take place at longer distances from the jet base, where the volume of the jet is simply higher. So at those scales, we expect the jet to be more hydrodynamical than magnetically dominated. So we also estimate how is the acceleration of the cloud because of this interaction, and we have into account that the cloud is being expanding from the heat seeded by the jet. This is a simplified numerical simulation of this scenario. We have like the supernova remnant, the supernovae exploding inside the jet. Here's again, and we can see that it starts to expand, and it will be accelerated by the jet, and eventually, as I said, the instability will disrupt the cloud. But before it is disrupted, this interaction might result in some radiation. And also you can see here that before it is disrupted, at some point the expansion of the cloud causes a complete obstruction of the jet of the AGN, so the morphology of the jet is completely affected by this very massive obstacle. Here, well, as some snapshot of that simulation, and what we did was comparing the evolution that we found of the cloud in the simulation with the evolution that we found with a simple semi-analytical approach that I described here. Here, this is like the semi-analytical approach of the acceleration and expansion of the cloud. And this is the numerical simulation. So we compared these two results and found that the differences are not significant. In white, I'm showing the semi-analytical approach, and in blue is the result from the simulation. In the case of the simulation, the acceleration takes a longer time, but the Lorentz factor achieved are more or less the same for both cases. So we use this semi-analytical approach to explore a more wide range of parameter space, which is an easier approach to go with. So this is from a dynamical point of view. I will return to this work in a few minutes. But now we wonder, well, this is the effect from the dynamical point of view. What about emission from this interaction? As I said earlier, we don't normal stars like the solar type main sequence star are not very important in this interaction, because what we need is a strong stellar wind that can impact or can resist the impact of the jet, because we will have like the collision of two fluids, and in this collision a double bow shock structure will form, separated by the surface discontinuity, and we expect that these shocks are able to accelerate particles up to relativistic energies, and these particles interacting with the different fields will lead to the emission of non-thermal radiation. Again, this is a very simplified view. Most of this work, the part of the acceleration of particles is treated in a very phenomenological view. At least in our work, we treat it this way. But it's like a zero approach to the part of the acceleration of particles. And this interaction can lead to different type of phenomena. We have from gamma ray flares of very short duration to longer lasting emission, and also we could have collective emission. This gamma ray flare have been proposed by Kangulian, also by Araudo and collaborations. The idea of this gamma ray flare of short duration is that an obstacle enters the jet very close to the jet base, so and are individual objects with very powerful winds, such as an O or B stars, that can lead to a gamma ray flare. This work here, they consider a red giant star entering close to the jet base, and part of the stellar atmosphere is removed by the tidal forces and also by the impact of the jet. And so these clouds produce a variability of a variability really fast in the emission, which has been observed in different blazars. So it has been this model has been proposed to explain the ultra-fast variability in some of these blazars that present very tight constraint on the power of the sources, and it's not clear yet how they can be produced. So this is a model that has been proposed to those events. As I said, we can have also longer lasting events, and this is the case, for example, of the work when we study the interaction with the supernovae. Here I show you the prescription we use to the semi-analytical approach, where we consider that the luminosity, the gamma ray luminosity we are going to observe from this interaction is related to the energy ceded to the relativistic particles by the jet. Here we put everything we don't know about particle acceleration. So as I said, it's a very phenomenological approach to take into account this mechanism. This term is basically the surface of the obstacle that is being heated or impacted by the jet. So here we include the expansion of the cloud, and this term takes into account the acceleration of the cloud and relative velocity between the cloud and the jet. And finally, we consider, as I said, a simplified approach to quantify the luminosity expected, where we put like a radiative efficiency of the interaction, taking into account the cooling times by the main radiative processes taking place. So with this approach, we computed the light curves expected from the interaction of a relativistic jet with a core collapse supernovae that could take place in star-forming galaxies. Here we can see that the emission lasts several thousands of years. It's shorter for more powerful jet, but still the emission lasts for 1,000 years. So it's that's why I call it longer lasting events. And on the left side, what we did was at the peak of this event, we computed in a more detailed way the emission, the non-thermal emission, where we put now a power law for the injection of relativistic particles. We consider only leptons here. Then we quantify the different fields, the photon fields. Basically, in star-forming region, a dominant photon field will be the the infrared field of the galaxy. But we also computed a synchrotron with several prescriptions for the magnetic fields, and we also included the photon field provided by the population of stars in this galaxy. And we can see here that the emission could be detectable at the peak of the event, but if we go to the semi-analytical approach and the light curves, we see that the level of emission is above 10 to the 44 for thousands of years in the case of very luminosity jets, but it's also above 10 to the 42 for more moderated jets. So although it's not very usual to find a supernova inside the jet, this luminosity is expected to last for several years, so the probability of finding this interaction is not negligible. We also studied the case of a jet interacting with a type 1a supernova, and this is the case. This will be the case for elliptical galaxies such as M87, where the population star is mostly old. And in this case, we also find emission lasting for several thousands of years. And here we computed again the luminosity of the peak of the event for a galaxy like M87. The values of the luminosity we found in the gamma range are not very high in comparison with what is already detected for M87. So this emission is almost negligible for a galaxy like M87, but we are not close in the possibility of finding this emission in other type of in other elliptical galaxies that are very abundant. In particular, a lot of AGN are associated with elliptical galaxies. So again, we hope to find just a very broad statistic on the population of AGN with elliptical galaxies, and the duration of this event told us that we hope to find approximately 10 of these sources in the local universe. So it's not negligible the possibility of finding this. The point is that if we find this, we are not we cannot distinguish this emission from any other gamma ray emission from the jet, because in gamma ray these jets are not resolved, so we cannot pinpoint exactly where the emission is coming from. So we won't be able to say exactly if this interaction is the one responsible for the emission in a particular galaxy. But again, it's a possibility. And in the case of, well, here I have shown you like very short flares, also longer lasting event during thousands of years, but we can also have collective persistent emission coming from the interaction of the jet with whole population of obstacles. In one of the first works that can be found studying this is Araudo and collaboration in 2010, where they study the interaction of the jet with a family of broad light region clouds that can enter the jet close to the base. The interaction with one or two or few objects can lead to transient event, but with more numerous objects where the variation of the number of objects inside the jet is approximately constant in time, could lead to persistent emission. A more recent work on this same interaction with the broadline region clouds by Del Palacio and collaborators show that the emission could be persistent, but we expect some fluctuations given that the number of clouds inside the jet at any given time might change slightly. So this interaction with whole population could lead to the persistent emission of gamma ray emission from this interaction. And in this same subject, we study, well, actually, a previous work by Hardcastle and also by Wykes, where they study the stellar evolution with different masses in the galaxy Centaurus A. They have obtained, it's changing. They obtained that the interaction of the jet with this population of mass of stars could lead to the diffuse X-ray emission observed in the jet of Centaurus A, but also can lead to the noted emission observed in this jet. So as I said, this interaction with the population of stars that in this galaxy could lead to both the diffuse and some of the spots detected in this radio galaxy. We performed a similar study. What we wanted to study was the influence of different type of galaxy host in the emission. Basically, we focus on elliptical galaxies where the main obstacles are red giant star because it has an old population. And we also study star-forming galaxies where the most numerous obstacles will be OV stars. And we study first the stellar evolution in the history of the galaxy to fairly have take into account the number of stars in the current time that will be inside the jet of these galaxies. And for the case of star-forming galaxy, we have as an example this blazar 33273, and we found that the collective emission of the jet interacting with the whole population of V star might be at the level detectable by CTA, although it's not very bright, and to be to these levels, we have like efficient acceleration and all the parameters very optimistic. So the emission is not very high, but we are close. In the case of an elliptical galaxy, we took as an example the very well-known M87. And again, we are close to detection with CTA, but this galaxy is already detecting gamma rays, and the levels we are expecting from this interaction is considerably lower. So it might be detectable for some nearby galaxies, but it's not. But we not expect very bright, persistent emission, at least from the result we have obtained. So these are some final comments. I'm not sure how much time I have, but these are some final comments on this work. We have seen that the presence of stars or other obstacles inside the jet can have an impact on the dynamics of the jet. It can decelerate it, at least for weak jets, for jets with luminosities below 10 to the 42. The mass loading by the stellar fields can decelerate the jets. We need different mechanisms to decelerate more powerful jet. And the interaction of this, besides the dynamical effects on the jet, can have a radiatively impact, where we can have different type of emission, from rapid, very high energy variability, to longer lasting events and collective persistent emission for the case of the jet interacting with whole population of obstacles. So this interaction, I think that they are very interesting because they could take place because the regions where jets are propagating are very complex, and they can result in a very wide phenomenology to be included in our works. So this is all for now. Thank you very much.
Great. Thank you, Florencia, for your presentation. Very clear and very interesting work. We have some questions.
Should I stop sharing, or
you need for answer the question?
Okay.
Yeah.
Yeah. So can I start, Maria?
Yes, sure. Go ahead.
Thanks for a very clear talk. It's very didactic too. My question is about the supernova, the case of supernovas type 1A, in order to this system to explode inside jets. Is it not problematic that the jet will destroy the accretion process?
No, actually, we don't expect that, because the stagnation radius of using the wind of the precursor of the supernovae type 1A, the stagnation radius is outside the system, the binary system. So we expect that the system is protected by this by the stellar wind already. So it won't interfere in the accretion process and the subsequent supernovae explosion. It's a very simplified view. We haven't performed simulation to actually confirm this idea, but we consider that the system is protected by the wind of the star in the binary system.
Thanks. I have more questions, but I'll let the colleague first for not cutting line.
Juan, you have a question?
Oh, yes. Can you hear me?
Yes.
Okay, I have a question. Thank you for the talk. Very nice talk, very clear. And if as you mentioned, this mechanism is probably a very good alternative when you have constraints on the power of the source. For instance, you have a jet power, then probably this could be more efficient to produce the required radiation or the observed radiation of certain sources. What can you say, for instance, if in the case of if you want to produce neutrino, probably the most typical scenario would be via the photohadronic process in jet, if you consider this case. And but there is also this mechanism that you propose in this presentation. So can you say something about, well, for in the case of production of neutrino by obstacles, like you described, probably the more appropriate mechanism would be the proton-proton interaction. So my question is the following. what do you think would be the most efficient mechanism for production of neutrinos? For instance, if you want to reproduce the observation by this blazer, the TXS blazer.
Yes. Well, actually, that's work in progress. That's why I haven't shown you, because I don't have any results yet. But yes, your question is very on point. I'm not sure if I have some of these extra slides for this, but yes, actually, this is some of the work in progress that I'm working right now. Because the problem with the photoadornic interaction, that is probably the most the favor mechanism for the gamma ray emission in jets, is that the same photon field that interacts as a target for the photoadornic interaction and the subsequent neutrino emission is the same that absorbs the gamma ray radiation. And in the case of the blazer, the neutrino flare was detected at the same time of gamma ray flare. So that result might be at tension depending on the emission of the gamma ray detected. So an alternative scenario is the one that you just said, is the interaction of a jet with a cloud, where the proton-proton interaction could be a plausible mechanism for explaining the neutrino emission, and it doesn't have the problems of having the same photon, the same target for the emission of the neutrino and also the absorption of the gamma ray that have been already detected. So it's an alternative, but I don't have any results yet, but it's a work in progress of this. Yes.
Okay, thank you.
Can I make a question?
Yeah, sure, Betty, go ahead.
Hi, Florencia. Nice talk, thanks. I have a number of questions and comments. One comment is on theoretical issues related to the stagnation point of the wind and the jet inside the jet flow. This is basically based on the fact that you might expect some equilibrium between the ram pressure of the two flows, right?
Yes.
But this expression, actually, you have also to include other effects like the pressure, the thermal pressure and the magnetic pressure if magnetic fields are considered, right?
Yes.
Let's forget for a while the magnetic pressure and only take into account the thermal pressure. And at this stage inside the system, I don't think that the flows have time enough to achieve the stagnation point, right? So probably the pressure...
Sorry, excuse me, why they don't have time? Sorry, I didn't understand that.
Yeah, because you have these interacting flows, right?
Yes.
Then you need some propagation of the wind inside the jet flow, but all this stuff is being swept into the environment, right? And it changes a lot. So you have to take into account that the left and right hand side of this balancing does not only include the ram pressure, but also because it comes from momentum conservation, so you have also the balancing of the important forces here, and in this case you have the pressure, and the pressure may be important, and it may be even more important than the relative ram pressures, because you have this immersed in the flow, right? So in this sense, this might have some effect in the balancing in the balancing of the analytical stuff that you got, right?
Yes.
I couldn't see the equations because it was too fast. So, but anyways, I wouldn't say that it's wrong, but maybe this term may be important there, right?
Okay. Just a comment on that. The expression I show here, I think is about here. It's only no, it's not here. Here.
I think it's before. It was before. This was still in the winds.
Sorry. Oh.
Yeah, it's around there. Yeah, I think it's
right. Well, I could look for it in a minute. But the idea is that this expression is only valid for larger distances from the jet base. Maybe I didn't say that. Where we expect that jet is hydrodynamical dominated. We are not, at least in our works. Probably some of the works that I show here of the short flares where the interaction is taking place in the jet base, the approach is different. But in our work, when we study the interaction far from the jet base, we consider that the most dominant term is the run pressure of the jet.
Yeah, but even it's hydrodynamically dominated, the thermal pressure is important if the stagnation point has not been achieved yet, right? And because they are both, in this, because they are propagating, that there is this very fast underlying jet flow, and I think it takes longer for them to reach this condition where the run pressure term is dominant over the thermal pressure term, right? And so this is something that you perhaps could consider if those pressures in both flows are of the same order, and then you can cancel on the left and right hand side, and then you end up with the only the run pressure term, right? So this is a theoretical consideration. The other part is with regard to magnetic fields. Okay, you are in kinetically dominated region of the jet, so you in principle you are saying the dynamical effects of magnetic fields are not important, but there is also the contribution from the wind, from the stellar wind itself, or the supernova remnant wind. And this part, even though it's actually you have contribution from both of them, but even though the contribution of the jet itself is not that important, the one that comes from the surroundings might be important, and also you have compression effects that might amplify the magnetic fields there, and at the end these contributions may be important as well. But this is another approach, another story, and it's
but you are right. Those contributions might be important, but we haven't taken them into account yet in these first works of the supernova interaction. But yes, you're right. Those contribution and magnetic field amplification by the supernova itself might be relevant, and we haven't included them yet.
And then also to preserve the supernova remnant, for instance, it's important, right? Because this the shielding effect of the magnetic field may preserve the supernova remnant structure itself longer. So this might change a little bit the dynamical time evolution of this stuff. And finally, I just would like to comment that we have numerical simulations where we account for the supernova wind or star formation and starburst or supernova wind interaction with the jet in the interior of star-forming galaxies. And what we essentially found from these simulations is that the supernova explosions, because we explode supernova in the region of the galaxy, because you have this interstellar median supernova, etc. So we have a supernova star formation rate that drives the rate of supernova explosions in the galaxy center, and then these will drive the wind that will in turn interact with the jet outflow. And what we have found out of these interactions is that the material that is entrained from the interstellar medium into the jet is swept very fast and evaporates as well. So this structuring is very hard to identify within the jet channel, because all this material is swept and evaporates, right? So it is, at the end you have a hot gas that, okay, it's prompt to high energy emission, X-ray and gamma rays. We did not analyze yet emission, the emissivity of these in these simulations. Actually, we have some of these simulations are published, but we are still working on this right now, implementing the emissivity part as well. As a matter of fact, is my student who is working on this is William Clavico, and he's also attending this lecture. But so from these simulations we have this, right? We have this evaporating stuff, and as you said, it's very hard to distinguish what is contribution from these interactions and what comes from, jet dynamics itself. But anyways, I would like to know your feedback on this. And
thank you. Yes, thank you very much. I will check those work because I wasn't familiar with them. Regarding the effect of magnetic fields in the dynamics of these jets, I think that last week or 10 days ago it was published an article with similar simulations to the ones I showed you earlier, where they studied the jet mass loading by stellar fields, but they included the effects of the magnetic field of the jet, and they found that the magnetic fields help to keep some integrity even for weaker jets. But I haven't time to include those results and studying them with more detail than that. But including the magnetic field might preserve some of the integrity of the jets, even with a whole population of stars losing material inside the jet. So yes, I am going to check the works you are telling me, because I wasn't familiar with them. Thank you. And thank you for your comments.
Oh yeah, you were welcome, and we can keep in touch, right?
Yes.
Okay.
So I have one more question, but before my question, just a comment on the Betty's comment. Because she said it's not possible to form a stagnation point. Is it confirmed in the simulations?
No, I'm not saying that it's not possible. I'm saying that this has to be verified because of the pressure, right?
So, but the simulations, I think they show this system or no? It's a question.
Yes, yes. Actually, they show the case that I show you here is. Everything happens so fast with the supernovae, but at the beginning of the interaction, we can see that that the supernovae start to expand actually before it starts to being accelerated by the jet. Just a moment before it starts to being accelerated is where we consider that the stagnation point has been formed, or the equilibrium has been achieved.
Time.
Yeah, but everything with this is very accelerated, and I'm not sure if it can be appreciated, but considering the conditions of the propagation of a supernovae remnant inside the jet, we found that the supernovae will be expanding a longer time than it will be expanding in the terrestrial medium, and after that it will achieve the stagnation, the pressure equilibrium, and at that point the jet will be accelerating the super. It's not very clear. And sorry, I don't have any simulation, nicer simulation to show you.
I know, but it's okay. At least it shows that maybe there is time. And And one question for the case of the interaction of the jet with the winds.
With what, sorry?
With the winds of massive stars, I think you talked in the beginning. I don't know, maybe I'm thinking about the forward shock. I don't know where you expect the acceleration of particles to be more effective in the forward or the other shock. Because maybe in the jets, the magnetic field is too strong and it gets parallel to the shock direction, and it will not allow the particles to cross the shock.
Yes.
It can have this effect of reducing the efficiency of the acceleration, the forward shock, and only the reverse can be more efficient to accelerate particles.
Yes, all of what you are saying is extremely important, but we have now distinguished between the morphology of the different shocks. And as I said, our approach to particle acceleration is very simplified, and we only consider a phenomenological point of view. Araudo and collaborator in those previous work in 2010, I think that they made a more throughout study of particle acceleration and the characteristics of the shock. And if I remember correctly, I think that the reverse shock is the most efficient for the emission because of the forward shock. I think it was a radiative shock, so it won't be very efficient for accelerating particles and in the emission produced there. But our approach was very simplified in that issue. Yes.
Thanks.
Okay, we have a question from William.
Yes, hi, Maria Victoria. Hi, everybody. Florencia, nice talk. Thank you for your talk. My question is, I have a set of questions, but I want to begin with. I want to ask you, what is the time scale of the deceleration that you are measuring in your simulation? You show for us a plot of velocity versus time for the deceleration of the jet, isn't it?
You are talking about this plot? No, deceleration. Sorry, I didn't understand that.
V versus T. So you.
Sorry.
It's V versus T, but I don't know. So.
This one. Sorry. Yes, at the beginning. No,
it
wasn't.
Yes,
those are my simulations. Those were performed by people from Valencia University. This one.
Okay.
I think I can. Let's see. Oh, I don't have the time scale here. Sorry, and I don't remember in what time they were decelerated, but I think it was in kiloparsec scale. They were already more or less decelerated because they say that they reproduce more or less the FR1 phenomenology, that the jet is already expanded and disrupted by kiloparsec scale. I think that here the plot ends 800 parsec, sorry. But I don't know, I don't remember the time scale for this.
No, yes, it's because we are studying the feedback between the jet and the star formation, as Bechi said, mentioned. So we are interested in to know how the material that is in the environment is being accelerated in the launching of the jet. So there are some events of star formation, supernova and supernova explosions that are very close related to your study, but we are studying the kiloparsec scale of this event. So we are studying how the material is being accelerated by the jet, the first stage of the evolution. So my question is, are you considering cooling in the simulations, and why that question is because the time cooling of the material that is being accelerated by the supernova explosions can be very short. So this material could eventually cools very faster, and this I think that can constrain the observations can to if we can to study how these structures are being accelerated out and how these cooled structures are being accelerated by means of the observations. We can constrain for example, how some of the history of the feedback of the galaxy. So I think that the cooling of the structures is, I think, that is important. Are you considering cooling in your simulations?
These people, this simulation, I think that cooling is taken into account. In our case, our study is mostly focused only in the region of the interaction, and the part of the evolution of the dynamical evolution of the obstacle was only taken into account to have an approximation of the evolution of the Lorentz factor of the cloud. So the dynamical evolution of the jet in our simulation is very simplified because we are not studying that in particular, only how it can be affected by the presence of an obstacle there. There we only have computed the mass load by the interaction with the star, but we are not considering a lot of effects that have to be taken into account to properly study the evolution of the ship. But these people here, Perucho and collaborators, are considering cooling, and these are the same people that published the paper a few days ago, including now the effects of the magnetic field. So maybe you can check on that. One question regarding your comments, you are saying that you are studying the contribution of supernovae, but you are at kiloparsec scale in star-forming galaxies. As I understand that the disk where the star formation rate is high in the stars is very narrow, quote unquote narrow. It doesn't go beyond kiloparsec scale. You are considering the interactions close to the jet base, and then how it affects the propagation.
No, but it's because we
actually, can I clarify this point? Actually, our environment is within 1 kiloparsec, so it's the nuclear region. So we start from the launching region at parsec scales, and then but the nuclear, we incorporate all the galaxy contribution within a box of 1 kiloparsec. So we allow the jet to expand above the disk of the galaxy up to the halo. And the halo goes out to 1 kiloparsec, but everything happens inside in the inner 1 parsec region in the nuclear region. It's just this point. But, you know, the fact that some of these star-forming galaxies, even Cepheid galaxies, they do show low temperature, dense, very dense structures floating at the jet at distances of, let's say, 1 kiloparsec or dozens of parsecs away from the center, is a clue that something is happening. You know, material is being entrained and carried all the way downstream to the jet, with the jet, or that could be these broadline region clouds or stars, right? Star-forming regions that are swept somehow and they are sitting there. So like it has been seen in some of these systems that you pointed out. And the stars themselves could be there. So we don't know. Only that the simulations show a lot of evaporation. So it's very hard to keep or only accounting with this swept material from the interaction of the galactic wind with the jet itself material, right? So the products of star formation, supernova, remnants, and explosions getting entrained in the jet, only this material, according to our simulations, these are MAGD with the magnetic fields as well. And according to our results, we cannot say, okay, it's very hard to see how these structures survive up to these very high altitudes because of the evaporation that I mentioned before, right? So this is the point. So stars could be, you know, if they are swept and survive.
And survive, yes.
Yes, exactly. This might be a possibility.
There might be a possibility with looking into, yes.
Yeah. Okay. Thanks.
Thank you.
Yeah. Only to finish, only to mention that that we are studying a scenario that mimics, for example, an ultra-luminous infrared galaxy. We have also the presence of the jet, but we have also a nuclear region with a high star formation rate. So, of course, we have interactions between the supernova explosions that enters into the trajectory of the jet, and that's why my question about the cooling and all this. So, but thank you for.
Thank you.
Okay, we can stop the transmission now, and we can keep discussing in the Google Meet, but we can finish the YouTube reshare.
Thank you again, Flor.
Okay.